Hello, Mr. and Mr. Ryan, all right? Yeah, we have talked about divide and conquer yesterday, right? Divide and conquer. So, we have a big problem, and then we divide it into smaller chunks of work, and then we can distribute them, yeah, to solve them individually, independently. And remember, we have a few numbers, yeah, a few numbers. We divide into two halves, and then we get the maximum of the first half and the maximum of the second half, yeah, and then we can merge them, right? This is the same idea as the merge sort, yeah. So one advantage of this divide and conquer is that we can do this small task in parallel. So in parallel, what's parallel? So I have a task, I can do this in parallel. In parallel, yeah, I can do this task. I have a task, I can do this in parallel, and then when this task, the results for these tasks completed, I can merge it to a big, to merge it to get the solution for the entire big problem, right? So if we parallelize this, we can achieve this performance speed up, right? Performance speed up. You know, the computers have cores, yeah, CPU, central processing unit is the brain of computer, yeah, brain of computer.
They have 24 brains.
Yeah, my computer have 24 cores, CPU cores, yeah. So each core is like a brain, okay, brain. So look, if a task can be done in parallel, right? For example, if it's fully parallelized, but let's say that there are 10 tasks. If I have only one brain, yeah, one core CPU to do it, for example, if it takes 1 minute to complete one task, then it needs 10 minutes to complete all these 10 tasks, right? But if I have two computers, and these can be taken in parallel, and how many minutes?
But there must be 2 people.
Okay, 2 people, two cores is the same, yeah? So how many? How long does it take?
One brain can't go out of your head.
Okay, this is just an assumption. Okay, so if you were the one people finish 5 coins, another people finish 5 tasks. You know, 5 tasks. So how long does it take?
It takes 5 minutes.
5 minutes, yeah, exactly. So look, if I have do this in parallel, so I can do this 5. Yeah, 2 brains, 2 cores, whatever. Yeah, and these are tasks or coins you pick, whatever. The time, yeah, 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, right? Because look, the time is shortened because these can be done in parallel. Means that once 1 minute passed and these can be done in parallel. That's one obvious way, yeah. One quickest way is to speed up, yeah, to get this performance speed up, right? It's easier, right? So look, if a task is if we have a lot of tasks to complete, and one easy way to make it faster is to get more cores coming to help, right? Right? Am I right? Yes? Make sense? Okay, so look, now we introduce this concept called the speed up. Okay, what's speed up? Speed up. Speed up is defined as the time of one core to finish the task divided by the time of n cores or n people to help divide the task. Yeah. So let's
it is equal to 10 divided by 5.
Exactly. Look, if there 1 people is 10, right? If 2 people is 5, then the speed up is 2, right? Easy. And if 10 people, this is 10 people, that will be 1, then speed up will be 10, right? Easy. Right? So let's speed up. So for this 100, if this task is 100% parallelizable, meaning that you can just this work you can just distribute it in parallel. That's called parallelizable, yeah. And then the maximum speed up is linear. Yeah, given these n cores, you can achieve the speed up of n, right? That's linear, yeah. That's the number of people, number of cores. That's the speed up, yeah. And then you can achieve this linear, right? This is linear. But in real life, the task compose sequential part and the parallelized part. What's sequential part? Means if I have a task, look, I have task. Look, these are the 10 tasks, yeah, 10 tasks. 10 task points, yeah. And if I say, okay, these 5, you can't distribute them in parallel, meaning that you can't have more cores helping to improve this. Meaning these 5 needs to be taken sequentially. But these 5, you can ask more cores or people to come to help. Right? Let's say 5 people to help. N equals 5.
Then it will be 6.
Wow, you're quick. Look, because this needs the 5, right? 1, 2, 3.
You'll take 5 and then you'll eat 1, and then the others will eat 1.
Oh, exactly.
And you're just taking 1 of them. So
Yeah.
1 plus 5 equals 6.
Wow, yes. Exactly. So look, the sequential part will be 1, 2, 3, 4, 5. And then the parallelized part, right? This takes 5 seconds, 5 minutes, yeah, whatever, 5 units. But now these can be taken by parallel by 5 cores, right? Look at here to here, only time equals 1. So time would be 5 plus 1 equals 6. Okay, so ideally we want this sequential part to as small as possible, right? So we can have more cores to help it speed up. And we want to have this bit, 100%, I say. Now it's just 50%, right? Because look, there are 10, and then 5 of them can be parallelizable, so this is 50%, right? So we want this percentage to go up to 100% to utilize the multi-cores technology, yeah? To have more people to come to help, right? So we're going to study a formula which has this sequential part B, and then if this sequential part is B, and then the part which can be parallelizable is 1 minus B, right? Okay? Because all these two added up to 1%, 100%, which is 1. Okay, let's do this. Look, speed up equals T1 divided by Tn, right? And I can do this again. Tn, yeah, Tn equals what? I can do this T1, and then it will be equals to the sequential part plus the parallelized part can be divided by n, right? Because look, this is the part which can be parallelizable, and then there are n process you can help to reduce the time to 1n, right? Okay, so look, remember we talked about B is the sequential part. So if P is the percentage that can be parallelizable, so P equals 1 minus B, yeah, right? P plus P equals 1, right? This is the part that can be parallelizable, and this is the part which cannot be parallelizable. So if we look, we can cancel out this. So it will be 1 divided by B. B will be 1 minus P, right? So 1 minus P equals P plus P divided by N, right? So look, this is the formula. The maximum speed up. Okay, I just look from here to here, right? Look, B plus P is the percentage that needs to be sequentially, executed, and the P is the part that you can have more people to come to help. These two B plus P equals 1, right? Okay, so if I substitute B with 1 minus P equals P, and then we get this, right? So this is the maximum. We call it Amdahls law. Maximum speed up. Yeah. Okay, so when P is 1, what does it mean? So when P is 1, let's substitute. When P is 1 means that this task can be 100% parallelized, but like the 10 coins, you can have 10 people to come, right? To help, right? So when P is 1, what's the value? 1 minus 1, 0. 1 minus n divided by n. So when P is 1, that will be becoming 1 minus 1, that's 0, plus 1 divided by n. And what's this value? This is 0. Yeah. 1 divided by 1 divided by n. What's this? What's the value of this? Ryan? Anyone? Ryan? What's the value of this? 1 over n. Yeah?
Yeah.
What's this? That's n, right? This is the linear, right? The linear thing we talk about. But if this P is what? 0. What happens if this P is 0? It's 1 divided by 1 minus 0 plus 0 divided n. Okay, so this is easier. Can you tell me what's this? 1, and what's this? 0 divided by n. N is bigger than 0, obvious. 0 divided by 100 equals what? 0. This is 0. This is 1, right? 1 divided by 1? 1. Okay, so it means that if no portion of the work can be parallelizable, and this is sequential, the speed up is 1, because these two are the same, right? Yeah, because if there are 10 coins, and you need to eat them, you need to complete them one at a time. You can't have more people, more calls to help you to shorten the time of this work. But this time will be the same, and the speed up will be 1. Right? Make sense? Yeah? So this formula, okay, so this formula computes the maximum speed up. If we use n calls, CP call or n people to speed up the work, the P percentage of work. P is the percentage of work that can be parallelizable, right? Yeah, that's the speed up. Okay, and the speed up is the time of using 1 people to do it, 1 cost to do it, divided by using n people to do it. Okay? Any questions so far?
No.
Any question? No? Okay, so to sum up, we want to have we want to design the algorithm, to have this bigger P of work that can be parallelized, right? If the work is like 0% parallelizable, then it can't be speed up by using multi-core technology. Yeah. Okay. Okay, that's it for today. Bye bye.